So in this problem, we're given that a ball of mass m is attached to a string of length L at some angle theta with the horizontal, and that this ball is traveling in the horizontal plane in uniform circular motion while being pulled around by this string. So the first thing we have to do is draw an isolation diagram. So the ball has a tension force pulling it up along the string, and it has the force of gravity, mg, pulling it down. I'm going to include acceleration in the radial direction because in uniform circular motion problems, it's very important to remember that the acceleration has to be directly inward. So now, the first thing we're actually asked to calculate is what the tension T has to be. And the way we're going to do this is by noting that the acceleration is directly inwards, which means that the sum of the y-hat components of the two forces have to add to 0. So what that means is that since T is at this angle theta, we have to have that T cosine theta is equal to mg, because otherwise they won't cancel out and the ball won't be able to move in that horizontal circle. That tells us that T is equal to mg over cosine of theta. And so now what we have to do is we have to check to make sure that that answer makes sense in the limiting cases. So as theta goes to 0, we know that cosine of theta goes to 1, which means that T goes to mg. So we have to figure out, does that make sense? If theta is 0, then that means that this ball is just hanging off of the rope. And if you count that as uniform circular motion, that's fine, but it has a radius of 0, so it's not really moving in a circle. So all the tension is doing is just preventing the ball from falling. It's just resisting the force of gravity, and it should indeed have a magnitude mg. Now if theta goes to pi over 2, then cosine theta goes to 0, which means that T is going to go to infinity. And this also makes sense, because if theta is pi over 2, and the ball is spinning completely horizontally with the tension force pulling it directly inward and gravity pulling it straight down. But what that means is that there's no, this T cosine theta term isn't going to exist, because cosine theta is going to be 0, which means that T is going to have to be supposedly infinitely large in order to still counteract the force of gravity that's pulling it downward away from that horizontal plane. So this also makes sense. Now in part D, we're asked to calculate the period. And what we need to remember is that the period of anything that is moving in a circle is going to be 2 pi divided by omega, the angular velocity. And the reason this is helpful to us is because this ball is moving in a circle, we know that the net force has to be m omega squared times r, the radius. Now the radius is just going to be this value right here, which is just L times cosine theta. So that means that F net equals m omega squared L, sine theta, not cosine theta. And F net is just going to be T times sine theta, because the mg and the T cosine theta canceled out. So those two sum to 0. So that tells us that T sine theta equals m omega squared L sine theta, which tells us that omega squared equals T divided by m times L. Now plugging in our value for T, this gives us mg over ml cosine theta, or just g over L cosine theta. Now if omega is then equal to the square root of g over L cosine theta, then we can plug that back into our formula for the period to get that the period is equal to 2 pi times the square root of L cosine theta divided by g.